Hello everyone. In this video we are going to talk about the K nearest neighbor KNN classifier, and it's a supervised learning method. I have a video under my machine learning playlist for it. You can watch the theory part of it. So here we're going to do it using Scikit-Learn. Therefore, from Scikit-Learn we need the neighbors class under which we have the neighbors.kneighbors classifier. So this neighbors is just more than the KNN, but this subclass of it is, or method of it is the KNN. And I also need data set here for basically training this KNN. And I want to get some data from the data set here. That's the good thing about the Scikit-Learn, that it comes with some training data. So when you want to play around with these methods and with these classifiers and these machine learning algorithms, you can have some data and you don't need to create some. The other thing I need is under Scikit-Learn inspection, there is this thing here for drawing the boundaries of the classes for the KNN decision boundary display that I need. I also need matplotlib for creating the plot. I need this method called listed color map, because here I want to use different colors for different classes. And then there is the new thing here called Seaborn, which is an additional plotting module in Python. And I use that to create an advanced scatter plot here. So this Seaborn here I need for this, as I said, advanced scatter plot. So the most important parameter, like k-means for KNN, is also the number of neighbors to count, right? So you need to know how many of the neighbors for each data you need to count their votes. And you can change this parameter. So here I set it to 3n. I can freely change it to any number I want. Now here I'm gonna get the data from dataset. I'm gonna load the data from this iris. And then the first two features of that, so these are data for flowers, and then the first two features I would use for my training data X, and then I use dot target for what? For the targets Y. So as I said, this is supervised learning. You need the training data and the targets, and this training data has a lot more than two features, but here for visualization, we're just gonna only go with the first two features. And then we also need, as I said, color maps. So here I'm going to use red, green, and blue. And then dark red, dark green, and dark blue. Here, red, green, and blue, we use them for the regions of each class. And then dark red, dark green, and dark blue we use for the training data sets. The next thing I need to set up for the algorithm, other than the number of neighbors, is the weights. So how would you count the votes of the neighboring elements, or in general? Do you use the distance or do you use the uniform? In uniform, everybody's votes count as one. So there is no difference in terms of whether a neighbor to a data point is close or further away. While in distance, the further they are from your point of interest, their vote counts less. So the distance means proportional to the inverse of the distance, not really distance, it's inverse of the distance. Here I use the distance, which is actually more accurate than uniform. And then what you can do, that I'll do here, is I go ahead and seems like here I'm doing something twice in the code. So let me get rid of that. And yeah, seems like I have copied some lines of code twice for some reason. It's not a typical thing. Okay, yeah. So the KNN, the k-nearing neighbor, as I said, it comes with the neighbors class, and then under that you say k-neighbors classifier. Then you pass to it basically the number of neighbors to use and the weights. That will create an object for you, and then you use the dot fit method and then pass to it x and y. Or instead of all of this, what you can do is you can go ahead and add that dot fit x and y right after that. Okay, so instead of creating an object and then passing the data separately, you can do it all in a single line like I did for the k-means clustering. But here I'm doing it in two separate lines, no difference. So first create the object, then pass the data, so it determines all the parameters. Now it is time to show everything. So the first thing I do, I want to show you the decision boundaries. So I create basically an axis and a figure, and then I use that decision boundary display. And then what I do, I pass to it this submethod called from estimator, right? Because I want these boundaries. This is a general boundary display basically function or class. So what you need is to say from what. This data of these boundaries coming from what? You say from estimator. And it says what estimator? You say this KNN classifier, CLF, that we have trained. What is your data? My data is X. What is the color map that you have? My color map is this light color map that I have. So break my data into a red, a green, and a blue subregion. Put it on this axis that I have created. Predict the data for each one of the data in X and put them in one of those three subclasses. And use the color mesh here. And then for the labels of X and Y, use iris features name 0 and iris feature name 1 for the Y label. Okay, and then shading auto. So many of these you can just eliminate. In this case, you don't have to use many of these, right? Basically, what you really need is up to here. This is the important thing, this part. The rest of it is just for adding labels and coloring and so on. So now this is going to draw the boundaries for me. And then on the top of the boundaries, you add your training data. Okay, so what you do here is use this special scatter plot from the Seaborn that we renamed as SNS. And here you say, well, go ahead and pass the data that are from basically all of the rows and column 1. Go ahead and pass it to X, and then basically the all rows and column 2, pass it to Y, and that is going to be X and Y. So these are the X and Y of the scatter plot. Then based on the names that you have for the targets, because this target has 3 classes, go ahead and apply a different hue to them. And then you need to use those color maps. Alpha here is for transparency of this. Alpha 1 means no transparent at all, and then add a black edge to the training data so it's distinguishable from the boundaries, because these boundaries are also red, blue, and green. The training data also red, blue, and green, but they're dark red, dark blue, and dark green. And to distinguish further, I add a black edge on the top. And then I can go ahead and add, say, hey, the number of neighbors I chose is 3, and the weights that I chose is distance instead of uniform. Right? So before I get to these methods, let's first look at the results. And then we're going to talk about what we are going to talk about these extra 2 methods. So let me go ahead and run it for you. There we go. So you see, this is my training data in this whole region, and it could broke it for me into 3 boundaries, right? The blue region is 1 class, green region is 1 class, red region is 1 class. You see there is some blue region within the red and green, and this like isolated island and so on. And again, as I said, these are the names for different feature different classes of flowers. And so here is with using, this is all my data, and using what? 3 neighbors for each data to count as whether that data belong to one class or to another class using distance. Now keep that in mind, or what I can do is go ahead and basically create a picture of this for you. And then we want to put them side by side so you can see some differences. So here I take a snapshot of this. Okay, and then I'm going to, I'm gonna add it to the paint, and then I'm going to repeat that with a different number of neighbors, right? So do it with maybe 5 this time and repeat that. And then I also would change the distance metric. So right now, this is what I have. As you can see, right? This is the weight is distance, and I'm using 3 neighbors. Now here, as you can see, I have what? I have 5 neighbors to count their votes, and what? And again, the same distance for weight. And then I'm gonna go back here and then keep that 5 and then change this distance to uniform. And I can repeat the experiment here. So here we go. This is uniform with 3 as well. And then I got all of these 4 different results, as you can see. And now we want to see whether I have basically big differences. So when I go from here to here, my weight is changing. And as you can see, this kind of uniform instead of distance will eliminate this small isolated island for this blue class here. As you go from here to here, so you keep the metric the same, but you add more neighbors. Again, you see that here, this island is going away. And if you look at the boundaries, now you see that the boundaries are changing. Actually, the boundaries become a little bit smoother as you go from here to here. And that is the property that you have with adding the number of neighbors, the votes count. You get a little bit smoother boundaries. And so these are the major differences, right? So going from here to here, basically, you lose that small island, you get more basically smooth boundaries, and that is what uniform and adding more classes do. But you might have some misclassifications, okay? So in general, we have to care about how many neighbors we should count and how we count their weights. In general, distance gives you less misclassifications, but at the price of having more basically isolated features, stuff like that. And also using smaller neighbors causes your boundaries to be a little bit more abrupt, and the irregularities, while here using more neighbors is kind of making the boundaries smooth. And that is, of course, the effect of adding more people and adding more weights, that they kind of cancel each other. So this is what you can experiment with. Now, the other thing I wanted to show you is your methods, and there are several methods here. I just show you 2 of them that are very useful, as I think. The first one is to tell you what are the neighbors for a specific data point for a specific location. So you can use the clf.neighbors, k-neighbors, of course, where definitely it counts those with the n neighbors that you provided. So if your n is 3, it's going to give you 3 neighbors. N is 5, it's going to show you 5 neighbors that are the closest or nearest. And then what is the class of a new data? So you can use the predict method, clf.predict. And here I'm using several data points instead of 1. And I want to know for each one of them, what is the class of data, okay? So here we go with, let's say this, let's put it back to distance, which I believe gives you less misclassifications with 3. And I'm gonna run these methods and I'm gonna show you some results here. So now you can see that it says, well, the distances and the indices of the three nearest neighbors for this data at 5 and 1.5 are 0.5, 0.8, and 0.9. So the data closest to 5 and 1.5, the data closest to it, they have these weights, okay? These are not the data points, these are the weights of the data points. Well, what are the data points themselves? It doesn't give you the data points directly, it gives you the indices of the data points. It says data number 60, data number 93, and data number 57. These data, and you can go and look at your X if you want. You can go look at your X, right? This X has a bunch of data points, and you can go to those locations and see what is data what is data number 60, what is 93, and what is 57 if you want. So it just gives you the index of those, right? So in our case, if we look at the X, let me show you. If I go ahead and look at X, right? Say print X for me. X is, of course, going to be what? A lot of big data, right? So let me go ahead and run this so we can see it. It's going to be a big thing here, right? But you see, it says squeeze text 150 lines. So these are all of those data, as you can see, right? And then what I need is to count in this X, what is the data at what? At row, as it says 60. So I can use a simple matrix operation here, right? And say what is print what? X at 60. So it is row 60 and then all columns, right? You can show me that one, and then you can show me the other guys too, which are basically, if we look at them, they are 93 and 57. So let's go ahead and add those. And that should give me my data points, right? So you can see here. One is 5 and 2, the other one is 5 and 2.3, and the other one is 4.9 and 2.4. Are they close to 0.5 and 1.5? Of course they are. Look at them. You see how close these 3 points are to the target point, to the test point, basically. So it is absolutely what? Giving you valid data points. And if you want, you can get this portion of the answer as a variable and then pass it basically to what? To this X, so you don't have to manually type it. But you clearly see that those data points are absolutely close to my target point. And then it says now 5 and 1.5 is which class, right? Let's go ahead and look. So it says, hey, 5 and 1.5 is class 1, 5 and 4 is class 0, and 8 and 3 is class 2. And if you look at this plot one more time, you can see that it absolutely does make sense to you, right? Because look, 5 and 1.5 is here in the green data. That's class 1. 5 and 4 is up here in the red class, is class 0, and then 8 and 3 is up here in the blue class, is class 2. Okay, so you clearly see if I put data here within these boundaries, it gives you the prediction absolutely right. So hopefully this video was useful to you and you learned how you can use a KNN method and classify the data and then predict and find the distances and everything that you need. Thank you so much for your attention. I'll see you in the next video.